Welcome back to the LLM Wiki. This is episode 5, and we are stepping into the third pillar of the series, Verify. For 4 episodes our wiki has been made entirely of words. Markdown prose, written by a language model, read by a language model. And prose is wonderful for coverage, and for human eyes. But last episode left us with an uncomfortable number. When we asked the model to find contradictions in its own wiki, it was wrong 8 times out of 10. Words alone cannot guarantee logical consistency. So today we give the wiki something it has never had, a layer of formal logic, a part of the system that does not summarize, but proves. Let us be precise about the problem, because it is easy to miss. A language model can write 2 wiki pages that flatly contradict each other, and write them both fluently, both confidently, in the same calm voice. Nothing in the markdown stops it. And as we saw, asking another language model to catch the contradiction barely works, because it is judging by surface similarity, not by logical form. 2 claims about the same topic look alike whether or not they actually conflict. So the move is not to make the language model try harder. It is to add a second layer, entirely natural language for everything the model does well, and formal logic for the one thing it cannot do, guarantee that the knowledge is consistent. This gives us a clean division of labor, and I want you to hold it as the spine of the whole episode. On one side, the natural language layer, summarizing, synthesizing, staying readable and accessible. This is what language models are genuinely brilliant at. On the other side, the formal layer, logic programs that do transitive reasoning, detect circular dependencies, and enforce hard constraints with absolute certainty. Neither layer can do the other's job. Prose cannot prove. Logic cannot paraphrase. But wire them together, and you get a wiki that is both readable and verifiable. Let me show you exactly what that looks like, in a system we actually built. Here is the concrete case, a wiki for an undergraduate AI course, built as 2 synchronized layers. On the left, the human readable side, a teaching protocol, 45 concept pages in Markdown, and the raw lecture material. On the right, the machine executable side, a formal ontology in Prolog, an auto-generated file of facts, concepts and prerequisites and lectures, and a handwritten file of rules. And the 2 are kept in lockstep by continuous integration. Every single edit to the wiki triggers an automated check: are the Prolog facts still consistent with the pages? Has anyone introduced a circular prerequisite? If so, the build fails. The loop between the readable layer and the provable layer is closed, automatically, on every change. And what does that formal layer actually buy you? Things the language model is genuinely bad at. Take a question every curriculum designer asks: what is the minimal sequence of concepts a student must master to reach this topic? Over the Markdown alone, that is a long, multi-hop chain of reasoning, and the model's reliability falls off with every hop. In Prolog, it is a single query, answered in milliseconds by transitive closure over the facts. Even better, one tiny integrity constraint, requires of X by X must fail, makes it logically impossible to introduce a circular prerequisite. Add a bad loop, and the knowledge base refuses to load. The cycle is caught not by hoping the model notices, but by the structure of logic itself. Now let us take this idea into a domain where a wrong answer can hurt someone: clinical decision support. The architecture is called KRD, knowledge, rule, decision, and it separates 4 concerns deliberately. A fact extractor reads the free text scenario. A knowledge layer, compiled from the wiki, holds the clinical evidence. A rule layer holds handwritten contraindications, the hard, never do this constraints. And a decision interface sits on top. The crucial move is this: whenever a hard contraindication fires, the system short-circuits straight to a blocking response that cites the rule, and never even calls the language model. The model is asked to reason only when it is actually safe to. And the benchmark tells a clear story. On 32 type 1 diabetes scenarios, we measured the unsafe suggestion rate. A pure language model was unsafe on 87% of them. Adding retrieval helped a little, 63%. A rule-only system dropped it to 19. But the two hybrids that combined the rule layer with the model reached 0 unsafe suggestions. And here is the part 1 love. The full KRD stack did it while making 47% fewer language model calls, because the rule layer blocks the dangerous cases before any generation happens. The point is not that this one architecture wins a leaderboard. It is that layer-wise auditability, being able to point at exactly which layer made each decision, turns out to be cheaper, not more expensive, than a single monolithic model. The same principle generalizes beyond clinical advice, to any policy that takes actions in the world. The pattern is a symbolic shield, and it sits at the very last moment before an action executes. The learned policy proposes a move. The shield checks it against the constraint set compiled from the wiki. If every constraint is satisfied, the action goes through unchanged. If any is violated, the shield swaps in a safe fallback. We tested this on algorithmic trading, against 5 categories of risk constraint, under both normal markets and synthetic flash crashes. The result, 0 violations, with under 1 millisecond of shield latency. And a critical finding from the ablation, training the policy to respect constraints reduces violations, but does not eliminate them. Only the runtime shield gives a true 0. The lesson is sharp: enforce hard constraints at runtime, not just during training. There is one more kind of contradiction we have not yet caught, the implicit one. Not two claims that are word-for-word opposites, but two that only conflict after several steps of reasoning, given some background knowledge. This is exactly where the surface similarity detector failed. So we built Neuro-Prov, which uses ProbLog, a probabilistic version of Prolog, to compute the probability that two memory items are logically inconsistent, given a set of domain axioms. On these implicit, type 2 conflicts, it reaches an F1 of 0.983 against 0.6 for simple key matching. And it does so 49 times faster, because logic inference over a compiled constraint set runs in milliseconds, while comparing every pair with a language model does not scale to the quadratic number of pairs in a real wiki. Sit with that speed number for a moment, because it is the whole argument for going formal. A language model has to do one full forward pass for every pair of claims it compares. In a wiki of a few hundred pages, the number of pairs is enormous, and the cost is quadratic and brutal. Logic inference over a compiled set of constraints is deterministic and runs in milliseconds. At the small scale we tested, that is a 49-fold gap. At institutional scale, with thousands of pages, the gap is several orders of magnitude. So formal verification is not just more rigorous than the language model approach. In the regime that actually matters, it is the only one that is even feasible. Where is this worth the effort? In domains where errors are costly and the right structure exists to exploit. Education, where prerequisite dependencies form a clean graph that Prolog handles natively. Healthcare, where hard contraindications, never give X with Y, formalize beautifully, even if the softer trade-offs do not. Law, where reasoning is non-monotonic, a later statute overrides an earlier one, which calls for a different formalism, answer set programming, rather than plain Prolog. And government policy, where the trick is to formalize only the settled parts, and to keep the genuinely contested parts as flagged conflicts, not as rules. Different domains, different logics, but the same core idea, that the high-stakes layer deserves to be provable. So here is the map of where we are, and where this is going. The completed work spans 3 columns. Natural Language Wiki, readable, but unverified. Prolog, for hard constraint checking and the runtime shield. And ProbLog, for probabilistic consistency. 2 frontiers remain. Answer set programming, with its non-monotonic logic of defaults and exceptions, and notice, this is exactly the medicine for those exception-dense domains where the wiki lost to plain retrieval back in episode 3. And deep ProbLog, which makes the logic differentiable, so the constraint weights can be learned end-to-end instead of set by hand. The direction is clear: deeper and deeper fusion of the neural and the symbolic. Let us close the loop with where we began. Episode 4 left us with a wiki that could feel that 2 claims were close, but could not prove whether they conflicted, a contradiction precision of 0.2. This episode answers it directly. Hand that same job to a formal consistency check, and it reaches an F1 of 0.98. The difference is not a better language model. It is a different kind of knowing, proof instead of resemblance. The natural language layer gives the wiki its reach and its voice. The formal layer gives it a conscience, a part of the system that can say, with certainty, no, those two things cannot both be true. A serious knowledge system needs both. And that sets up the final pillar. We have learned to retrieve, to compile, and now to verify. What remains is to constrain, to take this verified, structured knowledge and use it to keep an autonomous agent safe as it acts in the world. That is where the wiki stops being a reference, and becomes something stranger and more powerful, a living constraint oracle for a reinforcement learning policy, one whose guidelines can be revised without ever retraining the model. Episode 6, The Wiki as a Living Constraint Oracle. See you there.